design for how we design central heat pump plants using typically, mostly we'll be talking about CO2 today, and apply those into multifamily buildings. Multifamily building is really the model that we'll be talking about today. Of course, there's other building types. They have different load characteristics, so we'll kind of stay on multifamily buildings right now, or at least residential. And so really what we want to start with is that this is what we know today. Really started with a lot of research about 10 years ago, maybe a little bit longer. And over the last 10 years, there's been a lot of partners working in the US and Canada to really understand how to shift from boilers that have really, really high recovery rates into heat pumps. So a lot of industry partners, a lot of policy changes, and today we know really quite a lot, and we've gotten to the point where we can really adopt central heat pump water heaters across the industry. So with that, we'll really start looking at how we apply these onto a building. So the biggest change that we're going through with multifamily domestic hot water is that it's a shift. It's a shift from high recovery rates where you'd have, like a really strong gas boiler. We'd size it in, some number of MBTUs so that instantaneously we can create a whole lot of heat, transfer that heat onto water, and then give it to the building. Because we can basically bring in a big pipe of gas, light it on fire, put it under a water vessel, and efficiently lift the water temperature quite quickly, we don't really need a lot of storage. So what's the biggest difference with heat pumps is heat pumps have a much slower recovery rate. So the design strategy is to step back, understand the building, and use storage and build that storage in advance, and then give it to the building as the load comes out. So it's really all about understanding the load, and one of the best loads we understand right now is multifamily residential and workforce or retirement or various load patterns. But they're really well understood, and they're understood because there have been lots of buildings over the last 10 years that have switched to heat pumps. And they've been monitored by a number of consultants in the Pacific Northwest, primarily engineering firm called Ecotope. And in addition to that, the existing gas buildings have been monitored for quite a long time. So we got a pretty good library of kind of what the daily life of building looks like. And so it looks like a load path where we can see the top two areas in this graph are weekday mornings. And so that big peak is a morning where everyone's up and showering. And then the usage goes down as everybody leaves the building and goes off to whatever they're doing during the day. And then they return, and then there's a high use over a longer period at the end of the day. And then we kind of swing into an overnight condition, and the usage is very low in the overnight usage. And something special happens there that we're going to look at a little bit later. Weekends are very similar in the amount of water used. It's just used over a different schedule across the day. So as we start looking at a building, the key is to really understand the load profile. And maybe the first thing we do is understand kind of that standard weekday and the building type. And there's a number of ways that we can attribute that load in a predictive way as we size a building. In existing buildings monitored, this is pretty much what it looks like. This is a building in downtown Seattle. It's a renovated multifamily. It actually used to be an electronics wholesaler, the best wholesaler in Seattle, where you could go buy transistors and transformers and kind of all those fun electrical gadgets. back in the day when I was a kid learning about that kind of stuff. Today it's a multifamily building, and that's what it actually looks like. Big peak in the morning, little peak in the afternoon. And so really, as you size a day and you establish how many gallons of hot water are going to be used throughout the 24-hour course of the day, it really looks like this. And so maybe the first thing that we do is, if we have that big peak in the morning, that we really need to size primary storage at our full water temperature to cover that big amplitude of a peak. We can spend that low period in kind of that goldish, yellowish square. We can turn the heat pumps on at any time as we start using the peak. We can turn the heat pumps on to start recovering that primary storage. And that primary storage recovery can continue on through the day. Usually by that second peak, we'd like to have the primary storage pretty well recovered. So when we look at recovery rates and we start looking at the specifics of how much primary storage, kind of that big tank of water, we'd want to be able to kind of size the heat pump capacity to recover it in maybe 3 hours, 4 hours, 5 hours, 6 hours, 7 and 8 hours, depending on the building type and when that secondary peak is going to happen, and if that matches up with a weekend profile. But essentially, that's kind of what we're doing. We're looking at how much storage we need on hand to cover that first peak draw, how much heat pump capacity we need to recover that peak in preparation for the secondary peak, and just to make sure that all flows through. If we can get that information and size a system based on those, we'll have a successful building, and we will. Sorry about that. We will be able to send that building throughout the day and meet basically the loads. So heat pumps have changed quite a bit over the years. And what we've found through recent study is that CO2 is really one of the best refrigerants for lifting cold water to hot water in a single pass. And there's just a couple of things about CO2 that makes that really quite effective. Sorry about that, forgot to turn off my office phones, jump forward. So the nature of CO2 is really quite different than most refrigerants. It takes on a supercritical condition, and that's really useful when we're lifting hot water. So if we look at the range of refrigerants that are typically found in the industry right now, it's rapidly changing with the new low flammability A2L refrigerants. But so far where we've come from is we have some fluorocarbon refrigerants. They have higher GWP, so that's a bit of a penalty for us. But also the 410A, 134, these refrigerants have a hard time working in colder ambience, and then at the same time working in colder ambience, delivering a really high temperature, output temperature off the heat pump. CO2 has none of those issues. It has a really low GWP, global warming potential of 1, and it will very easily lift 45-degree water to 150 up to 190 degrees in a single pass with very little energy input. It'll do that reliably in very cold ambience. And it's basically the difference with CO2 is it has all those refrigerant properties, and it goes through a refrigerant cycle where we'd normally go from, a liquid to a gas and back to a liquid, and just kind of go through that change and that phase change. But CO2 is a little different in that when it is placed under a lot of pressure, over 1400 PSI, it gets very hot. And in those conditions where it's both very under high pressure and very hot, it takes on a supercritical state or a transcritical state. And essentially what that means is it's still a gas, but it has the density of a liquid. So all that energy is just packed in super, super tight. And so it's a very hot gas, and And essentially what happens is if you run that through a gas cooler rather than a heat exchanger, a gas cooler, essentially what we're doing is expanding that gas. And as it expands, it cools, but it has to place that heat somewhere. So we show that heat onto a little pipe of water running through, which is kind of the classic heat exchanger. And then this could be a double wall heat exchanger or a single wall heat exchanger. They're all different. This is just properties of CO2. And essentially in a small unit like the Sanco 2 unit that I'm really quite familiar with, we can see that essentially as we show that heat, we put the CO2 under a whole lot of pressure. It lifts up to 105 CS, 105 C, so it's really, really hot. And then we just run that water in an opposite direction of the high temperature gas through the gas cooler, and all that heat just transfers over to that little pipe of water. As it transfers over to that little pipe of water, it works incredibly well. This is not just this particular heat pump. This is really how CO2 heat pumps work in lifting water temperatures. So on the extreme ends, we can see the lower right-hand corner of this particular slide shows a -14 roughly. That's kind of where that green and green and red dot meet. And so that's in Fahrenheit. So -14, pretty cold. It'll still work colder. It's just this condition is measured in this way. And we still have about a 1.75 COP in operating that heat pump. As the temperature increases and we start getting into the 40 and 50 degree range, we approach a 4 COP. And we have full capacity at this, that top blue line that's running kind of horizontally is the capacity chart or the capacity performance of this particular heat pump. We have full capacity running from right to left in all these conditions, maybe a little bit less capacity in -14 conditions, just because the thing's running a little bit slower. We've got some conditions to work through. But as we start approaching the 65 and 70 and 80 degree Fahrenheit conditions, the COP goes up to 5.5. It's really pretty amazing. In all these conditions, we're delivering a full output temperature of 145 to 150 degree water. And so there's really not another refrigerant right now that will span these. There are propanes and other refrigerants that are coming on that come close, but they still won't work in the cold ambience and deliver the high temperature, at least in my understanding today. So before we jump on and start really taking a look at how the single pass system works and how we deploy these, maybe we'll just pause for a second and see if there's any questions that we want to jump back to. Doesn't look like there are, so we'll just take a breath, keep going. So just back from the AHR show in Atlanta the last couple of weeks, and what was revealed that as we're converting to heat pumps from our existing methods of creating hot water for buildings, multifamily, commercial, hospitals, schools, whatever we want to apply. I'm just really familiar and kind of focusing on multifamily today. There are lots of heat pumps coming, right? Word has reached the industry globally, and there are more heat pumps coming into the market. Some are large CO2s, like we see there. Those are new entrants. The second one down, Mestec, actually started their CO2 journey about a year ago, and now they're getting ready to release product. A number of new CO2 products coming out, and along with those, because we have, there's various ways to lift water. On the right-hand side, there's more synthetic low GWP refrigerants like 513A. I know some R290 is coming also. And so there's going to be a lot of choice in the industry to kind of use heat pumps to make domestic hot water. We, as a company, I've been working on this for a number of years. And essentially what we've been able to do in all of our early projects, and we've done lots and lots of projects where we've converted gas boilers to heat pumps. Here's one in downtown Vancouver, BC, 1075 West Georgia. It's completed in 2021, started up in 2021. It's a 33-story office tower. Our Canadian company's accountants are actually in that tower, so I can, every once in a while, if I go get my taxes done, I can run to the washroom there and check, make sure there's hot water, and there is. So the way that building was done was we looked at the plants. There's one plant or an existing boiler configuration in the top floor, up in a mechanical room, and then there was also one in the parkade. The distribution lines were split, so it was easy to tap into that. And with a total of 10 heat pumps, 10 of these CO2 heat pumps, and a controller and some primary storage and kind of all those goodies, we're able to retrofit that building and move it from gas to electric heat pumps. It's there, it's working quite well today. And it's a really, really simple system design. So now we're going to talk about how these things work. And the relationship is really heat pumps, one big one or a collection of small ones. In really big buildings, we could have a collection of really big heat pumps all working in series who are producing high temperature domestic hot water and sending it into that second cell, the primary storage. And the primary storage is going to hold it, and we're sizing the storage to meet what we understand the load profile is. And then it's going to get over to a swing tank. We'll talk about a swing tank here in a little bit, but this is the relationship. And in CO2, it's always the same. Drilling into the relationship between the heat pumps and primary storage, it's really simple. Doesn't really matter what kind of heat pump we're using. I'm very, very used to this configuration, so I'll really talk about this. But we start with this blue splash of water. So this is cold water coming in the lower right-hand corner of this primary storage tank. It comes in from the city at whatever temperature the city gives us to. Cold ambience, it's colder than in San Diego. So we maintain a splash of that water in the bottom. And so we've got a stratified tank right there. And that cold water on the left-hand side of that tank has a port going out, and that port is going to go feed the heat pump. So cold in, stratified tank. As there's a draw and the heat pumps are going to take some water and lift it and put it back into primary storage, the left-hand port supplies cold water to the heat pump manifold. One big one, bunch of little ones, or a bunch of big ones. Doesn't really matter. Relationship's always the same. It'll go into the heat pump array, get lifted from its entering temperature up to its finished temperature. And in this case, the finished temperature is going to be 150 degrees. As it leaves the heat pump array at 150 degrees, it's pumped into the top of the primary storage tank. So imagine there's nothing else going on the right-hand side. There's no building. We've just got heat pumps and we've got a tank. At some point, we run that circuit and we've taken all of the water out of that primary tank, imagining that primary tank is cold. This is startup, day one. The whole tank is blue because it's cold. We run that circuit and we start pushing in that 150-degree water into the top of the tank. And essentially what that does is just starts pushing that hot water all the way down. And it keeps pushing it down until it gets to the very bottom. As it gets to the very bottom, it looks like that picture right there, where we've got a very small layer of cold water at the bottom. There's going to be a control sensor that starts to sense the water leaving the lower left-hand port of that tank is starting to climb. We're starting to see hot water there. And when we see hot water there at a temperature, the temperature can vary depending on the system. In my case, I think I'm used to seeing that temperature be right about 120 degrees, something in that range. When I see 120 degrees coming out of that and there's no load on the building, I know that that primary storage vessel is completely full. So I can stop running heat pumps. And now I've got a primary storage tank full of 150-degree water. Okay, so we're ready to start the day. Next thing that's going to happen is there's going to be a draw from the building, right? So now we've got a load, and that load starts coming out of the building. Oops, sorry, jumped a couple of slides there. Went a little bit too far. Oh, nope. Okay, good.
Albert?
Yeah.
You have a question from Nick. It might be good to answer that before the end of the section. Do you see it?
Great. Okay. I'm reading your question there. Oh, yeah, good to hear from you, Nick. Cold water goes straight into the heat pumps rather than through the bottom of the storage tank. So we're actually going to just talk about that right now. So the layout is cold goes through the bottom of the storage tank. We keep the storage tanks stratified, and that's a really important point because of this slide. If I can get it to advance right here. Why aren't we advancing? There we go. Okay, so so this is a funny looking slide. Essentially what happens with CO2 is very, very unique. And we're just starting. So right now we've got a full primary storage tank. And we want to stop running the heat pumps because we don't want to give those heat pumps any warm water. They only really want cold. That's what they're very, very efficient at lifting cold to hot in a single pass with very little energy, a little bit of compression energy, a little bit of fan energy, and a little bit of water pump energy. And so when we look at this slide, essentially what happens is we are looking on the left-hand side, that red line is inlet water temperature. So right about 45 degrees. So see, we're seeing a steady line of inlet water temperature at 45 degrees going into this heat pump. Right about 4 p.m. or 4:30 p.m., that tank starts filling and we start seeing 120-degree water leave the tank and enter into the heat pumps. And this does get to why we use the stratified tank. So what happens when that temperature is elevated, the COP and the capacity on the right-hand side go down. And that blue line up there is heat capacity of the heat pump. So you can see as the entering water temperature increases, the capacity of the heat pump decreases. And if you think about this simple relationship, that this heat pump has a fixed 150-degree output temperature, and it's based on, and it's geared, essentially, it's designed to take 45-degree water and lift it 100 degrees to 145 or 150 degree, then that delta T between those two temperatures is the capacity of the heat pump. That's where we can actually place that energy. And so as we start decreasing the delta T of 100 degrees down to 80 degrees, 70 degrees, 60 degrees, 50 degrees, we start losing the capacity to actually place that energy because it's got a fixed output temperature. And as that delta T shrinks, the capacity of the heat pump shrinks. So right about here where the blue line crosses the red line, we really run out of capacity and the system really won't perform as designed anymore. That is indicated by what happens when you lose stratification of that tank. So if I jump back and I look at this slide, and I reheat the entire tank and I start getting high temperature water down here and I give it to the heat pumps, then it doesn't work. This is why CO2 isn't really a good refrigerant to do heating. It can do domestic hot water, it can do a little bit of space heating, but it doesn't do it very well. And here's why we're really looking at this is because in multifamily buildings, or really any building type, there's always a period of low draw, right? So multifamily buildings are really easy one to point to. This is an actual building in Seattle. This is actually a little higher than normal draw because this was senior housing. And so it's got a little bit different load profile than workforce or so forth. But essentially you can see the draw pattern, and that low little period of draw, which some periods of that are really quite low, there's just not much draw, yet there's a recirculation loop going on all the time. And if we take that recirculation loop and we pair it onto the primary storage, essentially what we're going to be doing is taking full temperature water out, running it across a mixing valve, sending it out to the building. No one's going to consume it. So it's just going to come back. And we do that over and over and over. And essentially what we're going to do is lose stratification in the primary storage tank. Once we lose stratification in the primary storage tank, we lose that cold water splash at the bottom. The heat pump starts seeing warm water, and the system starts losing its performance characteristic. And that great 4 or 5 COP will start falling down back down to 1 or 1.5 or something like that. It's always going to stay above 1, but it's not going to hit the numbers that we really want. And if we don't have the capacity, then that's going to affect our building sizing and our capacity to serve the building. So what we do right now is we place the tanks in isolation. And this is actually going to be later coming up in a Title 24 code change that's going to talk about maybe how we do this isolation. So now we're looking at the relationship of heat pumps, primary storage, stratified primary storage, and then the swing tank. And the swing tank or temperature maintenance tank is basically our way of isolating those recirc losses. So we'll set up a system where the primary storage tank is going to give high temperature water. It's going to send it to the building, but first it's going to send it to that isolation tank. And so that isolation tank, when there's a full draw in the building, is going to receive 150-degree water. So it's going to be full of 150-degree water. When there's a draw in the building, when there's no draw in overnight conditions, essentially what's going to happen is that tank's going to cool, because we give that tank full 150-degree water. It takes that 150-degree water, starts giving it to the building through a mixing valve. So we mix it down to 120 or a number. We send it out to the building. And when it's used, it just goes away. It goes down the drain, no problem. More cold water comes in and replaces it. In overnight conditions where it's just recirc losses, it'll go out to the building, it'll come back about 10, 12 degrees or 8 degrees cooler, and it'll come back in that tank. And now we got this little circle of all recirculation losses. Eventually what will happen is that tank will cool below its mixing point, because we'll just push all that volume out to the building, get it back at a lower temperature, and sooner or later the losses are going to catch up with us. So typically in that condition, there's some form of electric resistance or some way of lifting that independent isolation tank. So in this case, in a building like the size that we're looking at, it might have about 9 kilowatts of electric resistance to do a final lift. And when you need the final lift is when people start waking up and making a draw on the building. Then we're starting to pull water out, and it's going to go past the mixing valve and start getting used. It might be cooler. So when that draw starts happening, or during the final stages of the recirculation draw, the electric resistance will flash on, do a final lift, get it above its mixing point. And if we've got an electronic mixing valve, it'll very easily kind of accommodate the condition and mix in very little cold water to hit that target delivery temperature. And as it comes back, it brings all those losses back into that one tank. Here's kind of what it looks like. And when we size it, when we size a new building in some of the sizing tools that we're going to look at in a little bit, it will give us a prediction of kind of how that swing tank's going to behave. So real building, these are real results, similar building in Seattle. We can see that low overnight water usage on the upper left-hand corner of that graph, and matching down below, we can also see what the swing tank temperature, or that isolation tank. It starts out in this graph around 140 because there's been a draw. So it's constantly receiving 150 or 145 degree water. So it's nice and hot and full. And as there's no draw on the building, the recirculation losses start taking over, and we can see that tank temperature drop all the way down to 125. In some cases, it can drop below 125. It's just a function of how many losses and the volume of the tank and the duration of the cycle. And so what we see is going straight up, we can start seeing a draw on the building. So as we see a draw on the building, and in these conditions, the electric resistance may come on, it may not, it's still above 125 degrees Fahrenheit, but this is kind of indicative of the condition. As the load starts picking up, you can see the swing tank temperatures start increasing. And that's why we call it a swing tank. It's an isolation tank, but we call it a swing tank because those that are watching these things and designing them are essentially going to watch the temperature in the tank go through these wild swings depending on what the recirculation losses are. So to kind of round it out now, we'll say our new relationship, this is at its base, this is the relationship for CO2, certainly CO2 water heating in multifamily buildings. It's going to be the same for commercial buildings. It's all going to be just, slightly different in size per loads and uses, but it's heat pumps. Heat pumps are serving primary storage. Primary storage is sized to match the draw pattern. And then there's a swing tank or an isolation tank, and the swing tank and the isolation tank is there to isolate the recirc losses away. So back to Nick's question is, why can't we give the cold water directly to the heat pumps? Essentially, the way that this is piped is we've got cold city water coming in on the lower right hand, and it leaves the lower left hand, goes to the heat pump and kind of picks up. And so we've got, because we're sizing the quantity of primary storage to kind of match a load, this is how we, with a stratified tank, this is how we can kind of measure how full the tank is. We can just keep running the heat pumps, fill the tank from top all the way down to bottom. And when we see that temperature at the bottom start increasing, then we know we've got a full size. If the heat pumps are connected directly to city water, we can't really run that circle, right? We want to be able to, in a no load condition, like an overnight condition, where there's very little draw, just take the volume of the tanks, which may only be 50% full of full temperature water, or they may only be 25% full, but we want to be able to run that circle. And so that's why we connect city water into the stratified tank and then out of the stratified tank to the heat pumps so that we can kind of fill the primary storage from top to bottom. Hopefully that makes sense to everyone. So one last thing, and then we're going to go, we'll go through a little section change here and catch up on some questions here in a moment. While we're here, I just want to say that there's two different ways to do an isolation tank or a swing tank. And these slides are courtesy of NIA, and there was a TRC report here last week at the Advanced Water Heating Initiative commercial heating group meeting. And these were presented, and they're just a great way to communicate these two things. So primary in both the right section and the left section, primary water heating is the same. There's a heat pump. There may be something kind of topping it up. Maybe methods, maybe non-heat pump methods in topping up are going to kind of go away because they don't have high COP. But the primary, in this circumstance, the primary is the same between both. What's different is the left-hand side has essentially an electric resistance swing tank or a maintenance tank. And the right side is also same isolation tank. Rather than electric resistance on board in the tank, it's got just a multi-pass water heater. So that multi-pass water heater, depending on the size of the building and the size of that tank, could be a little tiny one, like a little, Ream 80-gallon unitary. That would work just fine in a little building, or in a big building. It could be a well-sized multi-pass heat pump that gets high COP, better than electric resistance. And in building types that have more risk recirculation losses, then why not change to a heat pump to reduce the energy consumption that electric resistance would use? So that's going to be kind of talked about in upcoming codes. Both these systems work fine. It's just a set of choices that we can make, because all we're trying to do is to maintain that parallel temperature tank, or the swing tank, as we call it. And then finally, we're almost done with this section, and then we can take some questions and bounce back and forth on it. Here's a job that we did in Delano, California, and we did exactly that. We developed through a tech grant, we developed a heat pump, placed it outside, uses CO2. This is actually, the building's up and running and occupied and all of that. And this was a little, you can see the room's got a lot of copper showing, of course it gets all insulated, but this building's got a full M&V kit on it. So we actually are gonna see every bit of water used, all the energy associated with that water used. So that makes the piping rather expanded, because you've got to have room to place all those flow meters and the BTU meters and things like that. But essentially this is the same story. It's the same as those earlier slides. Heat pump there in the left. That little middle picture is a 119-gallon tank. So that's primary storage, and that's full of 150-degree water. And then the little red circle is a Ream 80-gallon heat pump water heater. It can be operated in hybrid mode, or it can be operated in heat pump only mode. Just depends on what the recovery losses are that we can cover. If we can meet them with hybrid load, we'll understand that soon. We set it into hybrid mode right now to start off, but we could probably switch it back to economy mode. And same relationship. You could take that same relationship and transfer it onto a 300-unit building. Everything would just be bigger, still the same. And then the heart of managing this whole system is a set of controls. This is a project that we did in Seattle, Washington, and it uses a set of controls. Much bigger system, large CO2 heat pump capacity, a bunch of gang heat pumps together. All of those heat pumps are controlled by this controller here that we build in-house, and we have a wonderful guy named Peter on site starting it up. But essentially what the control is going to look at is it's going to operate the heat pumps based on the input of the conditions of the plant. So it's going to look at what the temperature of that primary storage is. There'll be a thermistor midway up on the primary storage. You can imagine that if you have a solid volume of 150-degree water and you start drawing on it, essentially what happens is, see if I can bounce back here a little bit. Essentially what happens is this, this cold layer, as you start pulling it out, we're not adding volume, and it kind of varies a little bit with the draw on the building. But essentially, as you pull hot water out, it starts filling with cold water until we pull that cold water, heat it, turn it into hot water, and it starts filling it back up. So that cold water starts rising. And as the cold water layer starts rising, it'll hit the thermistor. The thermistor will see it and say, "Oh, I need to run my heat pumps." And so that's essentially what that controller is going to do. It's going to look at tank conditions. And as tank conditions change, it's going to start up the heat pumps. And then it's also going to watch tank conditions at the cold water port going off to the heat pumps. And as it sees the tank condition change and we see hot water showing up at the bottom and starting to head out, that's when it's going to turn off the heat pumps. It has a whole bunch of other capacities and freeze protections and some logics and alarms and things like that. But at the high end, that's kind of the relationship of what the controllers are going to do. So now I'm just kind of looking at another screen here, trying to kind of catch up with the questions. Okay, Zach's question got answered. Can you just can you just oversize primary storage to increase the delta T? So I'm not sure I understand the question. I may not be able to answer it very well, but if you oversize primary storage, you're just going to have more 150-degree water available. And so that's a strategy. And that's a real strategy that's being deployed right now. I don't know that that's going to increase the delta T, because the heat pumps are essentially going to take cold water in from the city, whatever the city gives us, lift it up roughly 100 degrees or some number like that, and put it into primary storage. So when you oversize primary storage, that's where we're heading in California for sure. We're going to build excess capacity in primary storage, and it may not even be in the form of water as that thermal storage medium, because really that's how we're going to do load shift, right? So if you want to shift heat pump production to off-peak times, you're going to build more storage. You're going to size your heat pump capacity to fill that storage, and then you're going to tell the heat pumps and you're going to tell the controllers, don't run during peak, just wait, and then turn on, and you'll have plenty of room and plenty of capacity to build overnight or in off-peak times. So next question, is there a multifamily? Oh, Scott, all right. Multifamily, is there a solution for to allow for one sub-meter, then separate sub-meters for hot and cold water? You know, I only know how to lift. This is my weakness. I'm not really good at distribution systems and metering. I'm pretty sadly narrow focused in how to lift it from 50 degrees to 150 degrees and get it into the swing tank. And then what people do with it after the swing tank is, there's smarter people and more well-versed to that one. So I don't know that I could answer a metering question. Less thinking that heat pumps can't keep up, will run more often. Yeah, so that's when you undersize. I've watched a building get undersized, and when we get into the sizing tools, we're gonna assume that the load is going to be served by an amount of primary storage, and that to fill that primary storage with a heat pump, we're going to also assume a duty cycle, because we can't really expect these heat pumps to run 24/7. They're going to break. You know, there's a duty cycle, and duty cycles often, 66% of cycle time, which means when you start sizing, you're going to look at your heat pump capacity and say, hey, I've got to recover that 1,000 gallons in 16 hours on a 24-hour cycle, right? And that 1,000 gallons will get built up, it'll get used in the morning, and then we can rebuild it, and more will get used in the afternoon. But we've actually got to kind of size the heat pump capacity based on what the manufacturer's specification for duty cycle is. And when you, and so you can undersize a building, and that means that the heat pumps would run longer than the duty cycle. And we want to avoid that, because we're outside of manufacturer specifications. The heat pumps are going to fail earlier, and some of the heat pumps are, pretty big and expensive and hard to fix. Wesley, do you have an issue with inlet outlet sizes on the Rheem hybrid tank? Boy, that's a great question. We did. We actually were trying to build that project at the worst possible moment in time for global logistics of like how to get a water heater. And we originally specified like an 80-gallon, I think it's 80-gallon electric water heater with 3 kilowatt, because we didn't want to put a bunch of capacity in there, right? Because we're the efficiency folks, and so we're all about right sizing. So, but we couldn't get it. And so we, a great friend, Sean Armstrong in California, he was working on this project with us also, and said, hey, let's try a heat pump water heater. He kind of said that early on, and we flipped, and we found a heat pump water heater, and we actually had to break down the flow rates and really upsize our connections because it didn't have the 1.5 inch ports that we wanted. But we actually did a lot of calculations, or at least our engineering team did a lot of calculations to make sure that the pipes and all the piping would handle that flow rate. So yeah, that was something. So Zach's saying, does this system have CTA 2045 for demand response? It's being built in right now. Everything will have CTA 2045 for demand response. We've got a project in the shop right now that we're building these package plants for. It'll be one of the first, probably the first in California that has CTA 2045 and load shaping. And just fortunately, the plants were oversized, so we got extra primary storage, so we can actually use the CTA 2045 to kind of shape the utility load. Ted writes, are swing tanks only needed when there is recirculation? Well, yeah, I would say that's probably right. Probably have to think about that, maybe discuss the application, but swing tanks are there really to cover recirculation losses. So if you got a condition where we're giving 150 degree or whatever our tank temperature is out of primary storage, and it goes away and nothing ever comes back, yeah, you don't need a swing tank. You can just manage your flow and primary storage with that. Les says, thinking like cogen, it becomes more efficient the more it runs. Yes. Is there a wide range of duty cycles, and should that factor into the unit tank sizing? Yes, it should. We'll get to that maybe when we look at the sizing tools, which might be in, oh, it's the next section. Up next, sizing a plant. So here we go. Here's my redundant slide saying we're going to talk about sizing a plant. And there's new tools. So the exciting part of this for me are these new tools. These were developed with utility funding up and down the coast in Canada, Bonneville Power Administration, the whole Advanced Water Heating Initiative. This is one of the problems they wanted to solve was, okay, how do we really size a building with heat pumps? Because it's completely different than a boiler, totally different. Heat pumps is all about getting the storage right and matching the heat pump capacity to serve that storage based on what the load profile of the building is going to be. So the place you do this is accessible to everyone. It's utility funded, built by Ecotope in Seattle, and it's called the EcoSizer. It's got a lot of documentation, a lot of frequently asked questions. It's a really, really good site. Everybody can use this. We live on this site. And as you get better, there are things you can learn that you can really kind of get pretty deep into how you design a system. So, so starting with this is how it works. On the occupancy inputs, right, left-hand side of the screen, essentially we're going to be able to describe a building. There's two ways to describe a building, and we'll pick one. The profile that's light on the far left corner says total people and apartments. The next one is apartment size and occupancy rates. You can use either one. They'll give you good results. Right now, we're using number of apartments and occupancy rate. So studios, there's in this building, there's this super simple sizing. I think I did this when I was just building slides because it could be 50 studios. The occupancy rate, I did that drop down. You can kind of see it says ASHRAE market rate, but there are other choices. And there's a couple of California choices. And there's like a California market rate. And then there's low income, which might have higher occupancy concentration in it. So in any case, there's a set of numbers. And you can say 51 bedroom, 50 studios, 12 one bedrooms, 7 2 bedrooms, and then 3 family, 3 bedroom. And it'll assign an occupancy rate. We can change the occupancy rate, or you could even go in there and override it. If you say, I know my occupancy rate better than these guys do, then you can put your number in. And then the next thing that we're going to do is the next column over is peak gallons per day. So there's a number of choices. And it's super interesting because things are different and new buildings have low flow fixtures compared to old buildings. So you got to kind of think about this a little bit. You know, in a new building, there's a drop down where we can select 20 gallons a day. There is a California specification in there that's going to say 30 gallons per day per person. It's a number. We look at our site and we settle on a number. As a company, we do this every day, right? So we're using all of these numbers and we're trying to understand as much as we can about the building and then select the right number. And in some funding cases, you know, California is going to say, well, you got to use this number. All that's good. We give that data and then we flip to the right-hand screen and we say, okay, what's the city give us for temperature? You pick a number, you enter it in. What's our supply temperature? So what are we going to set the mixing valve? And as it leaves the mixing valve and hits the fixture units, what's that temperature going to be? Okay, we pick a number, 120, 125. You can run a scenario with 120. You can run the same scenario, don't change anything, change supply temperature to 125, and you can see how it'll vary because the next screen, as we start getting information back, is super interesting. And then hot storage. So depending on whose heat pump we're using and what its output temperature is, and then that's hot storage. The thing about CO2 is I'm really good at CO2 because that's really what I work with. There is no defrost. There's no defrost cycle that we need to deduct. There's no derating. I can literally say design temperature, supply temperature, and 150-degree fixed temperature. Doesn't matter if I'm in Vancouver, BC or San Diego, all good. I don't need to make a climate response. I'll pick a configuration for temperature maintenance system down at the bottom. I'm typically use a swing tank. It could be a parallel tube loop tank, right? So I could resize it for a unitary heat pump water heater or a large one. And then I could also say no recirculation, like the question we had earlier. And then I'm going to scroll down. There's a couple other questions, but essentially I'm going to pick a button and say, okay, I gave you my info. Give me your sizing back. And here's the sizing coming back. This is what it looks like. There's a little more detail, one more screen to look at. But that green arrow or that green line, basically there's a dot in that green line, and that dot basically corresponds to where the primary storage is. So that primary storage is a little over 400 gallons. You look down there and it's giving you an output number at the bottom of 420 gallons for tank volume for primary storage. Doesn't include swing tanks. Swing tanks is a separate deal. And the swing tank's down a little lower. And the swing tank in most, kind of average size buildings, like 50 studios, swing tank's always 120 to 300 gallons. And it doesn't really matter that much, right? Because there's ways that we can kind of give it more information about the recirculation losses, and that's what this is talking about. But over on the right-hand side is the swing tank resistance element. So it's saying in this building, based on a couple other things, I gave it kind of a rough number of 100 watts apartment as a recirculation loss number, right? So it gave me some feedback based on the input I gave it, and it's saying, well, you should give it 8.7 kilowatts or roughly 30 kBTU an hour if you're using a heat pump, something in that range. And California Title 24 swing tank volume, it wants to give it on the upsize because the Title 24 swing tank volume is really all about storing more and having less electric resistance consumption. That's changing a little bit. It's a little bit of a fluid relationship, I think. And then if we look in the details, up in the upper right-hand corner, that sizing, 50 at 1.54 occupancy rate or something like that, gave us 74.5 people. I guess one of them's short, like a youngster. 50 apartments, daily water usage. I stuck with 25 gallons a day. It could be 20, it could be 30. It's a number. It'll tell us what it thinks total hot water usage per day is. It'll tell us what the input I gave it. I did give it the 100 watts per apartment. And then I can save those results to a PDF. I hit that button, it'll give me a nice kind of feedback or a document I can share. But let's jump back to that graph with the green line running through it. So it's saying 420 gallons. See that blue dot below that? You can actually grab that blue dot and slide it. And if you look close at that screen, it says primary system storage 419.5, capacity 85.5 kBTU an hour. So it's saying I need heat pump capacity of 85.5 kBTU an hour to match that 419. And it thinks, it's telling me, saying, in your building, sir, to deliver that 419 gallon to match those conditions, the compressor runtime to at 85.5 kBTU an hour is 16 hours. So the interesting thing is I can take that dot, I can slide it to the left, I can slide it to the right. I can't build a slide to really show this, but essentially I'm saying I'm going to give it more heat pump capacity if I slide it to the right. And as I do that, essentially what's going to happen is the runtime is going to get smaller. I've got more heat pump capacity. And because I have more heat pump capacity, I have higher recovery. I can kind of live with a little less primary storage, right? Because sizing and serving the building load is always a relationship between how much primary storage you have and how much recovery you have. And as long as you stay within a reasonable compressor runtime, then, all's good. Other than that, I can also slide it to the left and say, well, you know what? Tanks come in 500 gallons. So I'm not going to find a 419.5 gallon tank. I'm going to get a 500 gallon tank. So I'm going to slide it over to 500 gallons. And if I have more storage, I kind of don't need that full 85.5 recovery rate. So I can I can live with a smaller heat pump. So with that blue dot and some experience, you can kind of tune the sizing of your building based on equipment or based on, maybe you just can't fit that much storage into the building because it's an existing building and there's only so much room. There's factors that you can use that as a tool to deal with. It's a really wonderful thing to be able to do. So now we'll jump to the next slide. And so this is another interesting part, because basically what this tool is going to do is it's going to predict how the building's going to behave based on the norms that we've all set up and the inputs that I give it. So on the upper graph, that's what our primary storage condition looks like. The green line is primary storage. And I start the day maybe not completely full. I guess maybe that day start is at midnight or something like that, right? So I'm still charging up the storage. So it's still hiking uphill until it hits that peak. And that peak is full primary storage. And then the day begins. And then pretty soon at about, 400 minutes in, people start taking a draw and we start depleting that primary storage. And so we watch the primary storage drop down very quickly. It doesn't drop down to zero. So yay. We size primary storage to meet this particular load. And as soon as it drops down to zero and people leave, then it can start rebuilding. If people are still there consuming water, if the heat pumps could be on and it's trying to recover itself, but the load is outstripping the recovery, right? So we don't really see it. We might see it where that precipitous angle starts kind of drifting off right where it hits that red line. And so, we've got some recovery going on, the load's softening a little bit. And so the tank doesn't deplete as fast. But as soon as that load's really kind of gone, the tank temperature starts hiking uphill again. until it goes back up to a peak at about, 1600 minutes or 1500 minutes. So it's probably more like maybe 900 minutes. I'm probably hitting that a little off. And then you can see the next draw pattern is much longer and much softer, right? That's kind of characteristic in standard multifamily residential of, people getting home at the end of the day, and then there's a slower period of draw for the multiple uses that people use domestic hot water. So at the next line down, let's look at the blue line. The blue line is demand at supply temperature. So, right, when we've got a full tank and there's no load on it, there's no demand. So the blue line's down at the bottom. And as soon as people start waking up and putting a demand on it, the blue line hikes up and it gets quite high. And we see the corresponding volume tank temperature kind of drop. And then when the demand goes away, that's when we see the green line start hiking up again. And then there's that low period of demand. And that low period of demand is what allows the heat pumps to recover that primary storage. So, that's kind of like what we do with capacity and cycle time. If we've gained that all right, then all that works. And then we can see demand starts climbing up and supply starts going down. And then we can start seeing in the hot water generation, the red line. Essentially, the red line is, watching our heat pump capacity, right? It's producing, it's filling primary storage, and then it stops producing. It's just resting. It's not functioning at all. So it's not burning any of those 16 hours in capacity. And then it turns back on, it runs for a while, and then turns back off, and then turns back on. Okay, so that's pretty simple. The next one down is the swing tank. So this is how we know if we size the building appropriately and size the swing tank. Because the purple line there is the swing tank temperature. And so, when it's fresh, and this is only, kind of showing part of the story, swing tank temperature should be seeing, 150, some high temperature water kind of come in. It's mixed throughout the tank and it's always got a recirc loss. So the swing tank will always be a little bit less than primary storage because it's got constant losses associated with it, but it should always be above our mixed temperature, our mixing valve temperature, right? So in this case, if it's 120, essentially what we're looking for is it starts the day at 130 because it's experienced overnight losses. Those losses accumulate, and we see the purple line is at the bottom of its V, and at the bottom of the V is where the electric resistance element turns on, right? That's that gold line. So it hits the bottom, it gets into the safety zone, electric resistance turns on, it runs, it lifts. Now we're at the top of the peak, and then it turns off. And then we hit another little recovery blip, right? As it starts cooling, the electric resistant, the tank senses that it's cooled, it turns itself back on, and then people leave, and there's a bit of a draw pattern and enough to kind of keep the supply running through the swing tank and giving it to the building for a period of time. Everything rebuilds and functions properly, and then people come back, and it starts, cycle starts again. And so what you're looking for here, right, if you're really trying to make the most efficient plant that you can, you want to see that electric resistance consume the least amount of electricity that you can. So that's all about sizing the swing tank volume, understanding what the recirculation losses are. And if you really want to improve it and you don't want to use the resistance element output kW, and you can see it's about a 9 kW, that's where it lines up across the top. If you switch that to some kind of a heat pump that can give, maybe 2.5 COP or something like that, then you'll cut that amount down. And because, the direction and the possibilities that we can engineer, that's a very likely solution. And so in smaller buildings, it was super easy for us to kind of look at using a unitary heat pump water heater. In a large building, we could certainly line up a nice 134A or a 513 and get that electric resistance expense down. So with that, we've kind of completed the sizing side. Let me check on the questions. Phil, hey Phil in Canada, how are you today? Does sizing tool consider efficiency of the HP based on outdoor temperature? It doesn't. And the reason it doesn't is because not because it's ignorant of the conditions in Golden, BC or anywhere else where it gets a bit cold. This particular heat pump gives really good capacity across ambience and doesn't have, and this is, the heat pumps used in these algorithms are among the best. And so it really doesn't take into consideration the climate conditions and the defrost conditions. When you look at a sizing and you say, okay, I need 85.5 capacity, kBtu capacity, then you actually got to go look at the heat pump that you're using and say, okay, if I'm using it in this climate, how, what do I need to do? Do I need to derate the heat pump in order to achieve that 85.5? So it's just looking at domestic hot water in the building, recovery and consumption, and then assuming that you're going to select equipment that will deliver that capacity requirement. Hopefully that makes sense to you. Less is the goal to size the system so that demand blue and useful storage are more or less in parallel. This shows much more storage made during non-demand hours. So I'm following. I want to make sure I understand so I don't answer it wrong. Is the goal to size the system so demand and useful storage are more or less in parallel? Yeah, I think so. I think that's a fair characteristic. And if I flip back to my screen and I go back to a sizing screen, so I've got capacity in the red, I've got storage here, and then I've got demand in the blue. And so essentially, yeah, right sizing it would be saying, this is how much my total storage and my consumed storage at the lowest point are within range. If I want to load shift, then essentially what I'm going to do is add more storage so that I don't need to immediately start recovery as we start using storage, and maybe that becomes more important. I'm not super familiar with kind of load shift in California, right? The Northwest is a little different than California and its vast quantity of solar PV, right? So midday solar PV is a great time to use all that heat pump capacity. Kind of late day is not. So if I increase capacity, I can kind of just live off of increased capacity and delay when the heat pumps will come on through capacity. And so on the other hand, if I shrink capacity, then I might not recover quick enough, and I certainly can't load shift. And if I increase capacity, then I'll just have more idle time. And those are a little bit budget and space considerations also. So it's kind of like a little, not a mystical mix, it's just a set of choices based on the efficiency goals that whoever's project and whoever's designed it is would have those goals. Hopefully that makes sense. And then I think I jumped. Okay, up next, codes. So this is fairly recent. I'm not the best on California codes, but this just popped out at the last commercial work group meeting. And so essentially, here's what they're saying, and they have wonderful slides that make great sense. So thanks, Nia, and thanks, TRC. Essentially, they're saying, okay, the system approach that we're talking about here is single pass and multi-pass. And we're going to look at a couple of situations, then it's going to actually give us kind of data. Single pass is primary heat pump equipment, single pass versus multi-pass, refrigerant type, capacity, temperature maintenance system, decoupled from primary or direct return to primary system, right? No swing tank, as we were talking about earlier. And so we'll jump a slide ahead. So very familiar stuff. And let me see if I can get my slides to move. Come on there, buddy. Oh, okay, good. Okay, so back to that slide that we looked at before, recirculation loop decoupled from primary storage. And that is so that we keep a constant condition in the primary storage where we have good solid stratification, and that stratification doesn't get disrupted by recirculation activity. So same. And I'm sorry, I'm going to go back there and say at this point, I think we're going to note this box up here is multiple heat pump water heaters or an auxiliary heater, because we could do that too, right? We could put a bunch of heat pumps in series, and then we could just throw massive amounts of electric resistance heat in it also to do some additional lifting. So temperature maintenance system return to primary configurations. Single pass return to primary, multi-pass return to primary, right? So these are systems that wouldn't use a swing tank. And so now we actually have some COP data based on research over these last few years. And essentially what stands out are these first two. You notice that the bottom says the refrigerant is CO2, because CO2 takes that supercritical state. It just uses less energy, works in colder ambience, and always delivers higher temperature water. CO2 is the best water heating refrigerant by far. Not great at space heating. It doesn't do any cooling unless you want to freeze something. So CO2 is really your best choice for water heating. Single family building, multifamily building, just anytime you want to add 100 degrees Fahrenheit or more onto incoming cold water, CO2 is the trick. So single pass in series for temperature maintenance, 3.91. And if that temperature maintenance tank goes away and we start losing the stratification, that 3.91 is going to go down a lot. That's why we're doing that temperature maintenance tank. Single pass, next one over, single pass in parallel for temperature maintenance. So that's another heat pump. There's little things about using another heat pump. The COP might not be quite as high. But those are really, really good numbers. And then we start looking at 134. And as we get into 134 and 410A, the numbers fall quite a bit. And so the question is, on this standpoint, from this standpoint, as the codes emerge and they're really trying to influence what the industry will put into buildings, then they do this valuation study and the COP study. This is across California climate zones. It says that they're off to the right, but California's, got a big range of climate zones. Tahoe exists, and Bakersfield exists, right? It's a big range. So essentially, when they decide what to develop code languages, I think this is kind of the existing Title 24 code. It currently allows single pass and multi-pass, requires a recirculation loop be decoupled from primary heat pump water heater storage or systems. And, I couldn't tell you if this is across all buildings, or you can create a case to not have temperature maintenance if you don't have recovery losses in a certain application. Plumbing configurations to ensure stratification in primary tanks. So that's really talking about that swing tank. Control requirements to achieve minimal efficiency, and controls are really important. That's where we design controls to maximize the efficiency of the system. Design documentation, operating conditions, performance requirements to joint Apex 14. We've been working that for a while. Here's maybe a proposal that they've been seeking comment on. And essentially what you see here is that they're getting rid of single pass and multi-pass. They're just saying we should probably go to single pass heat pump water heating equipment, and everything kind of builds on top of that. So revisions highlight in red, it would be really going to single pass rather than multi-pass because it is the most efficient. Single pass that meets require of NEA advanced water heating specifications for commercial heat pump water heating system tier 3 or higher. So there's a list being built. And typically, you know, for us in America, NEA builds the list. For those in Canada, usually the Canadian provinces, certainly BC, would adopt the list. There's a lot of cooperation going on across climates to develop that list. And so they're going to basically say single pass, temperature maintenance, and the equipment has to meet the NEA list. There's an alternative path in the 2025 code cycle, it looks like, saying you can use 2022 hot water recirculation, return to primary storage, no. Serious temperature maintenance, yes. Or there's an alternative path as you start choosing equipment that is the tier 3 or higher. So that's kind of what's coming up. So what that means to me is that all roads lead to CO2 for water heating as the most successful. Incentives as they come out, the incentives will probably offer more incentives to the most efficient systems, which will probably be CO2, single pass with temperature maintenance. And so really our next task ahead as we move through this is to get good at designing and implementing single pass CO2 with temperature maintenance system. So now let's actually look at plants, right? We've gone through how it works, how to size. Let's actually go on site and take a look. I've had a lot of experience in our group working with CO2 plants on site over the last few years. We've got lots of systems out, and I've learned a few things. One, and we also work with kind of AWI, Advanced Water Heating Initiative, and we try to help develop and implement those goals, right? Because that way we're really kind of targeting and building for the future. So we've got a lot of site plants that have been built, and they really have been successful, but we can do better, right? If you look at that plant, left-hand side is 1075 West Georgia, that big tower, and that rack system is in the upper mechanical room. It's a hot room, so it's a great place to place those heat pumps. They'll just soak up that heat, turn it into heat in water pipes, and then give it to storage, which is placed elsewhere in the room. In a existing building, that's a great way to do it because you got to cart all this stuff up, somehow get it into the room, and then assemble it on site. On the right-hand side is a new build in downtown Vancouver. And so those are 419-gallon tanks. So we got 400 gallons of storage, and we got a bunch of heat pumps paired to it. But it really fills a mechanical room, takes quite a bit of space, takes a long time to build. And somehow we have to teach designers to design, and then we have to teach installers to install, because it's not the simplest system, because the controls are really quite important. There are lots of systems coming on the line. Lars has been sharing really the key components of their system. So this would be a very large heat pump. It's a control panel paired with primary storage tanks and a temperature maintenance tank and a diffuser. The diffuser kind of goes into the primary storage and kind of spreads out and helps create that stratification. But essentially, this would be a site-built plant, right? So you got, and it's so big, it's hard to do it in many ways, because if you package that system and want to deliver it to a building, it's a pretty big package. Over the years, we started developing package systems, And the package systems were part of a goal in the Advanced Water Heating Initiative. And the goal is really to reduce size and complexity of systems, but it's also to reduce risk. Because as you look at designs as they come out today, there's a rather specific mechanical plan and a plumbing plan that uses all the piping has to be in the right place. You have to use the right check valves and make sure that the heat pumps can't overcome or are not able to overcome the pressure of a spring check valve. And you know, there's things you got to learn along the way. So part of what's going on, there's a couple of companies, ours included, that is developing package solutions. So what these package solutions look like is, rather than a site-built system, we try to compress it all into one skid frame, mount the heat pumps on it, place the primary storage inside. And so now we're just going to kind of take a look at what that looks like. We can do site-built systems all day long. Are they more efficient? Probably not. Are they more expensive? It's expensive to build something on site. And if it's the contractor's first time, there's a lot of risk involved because sometimes it doesn't come out right. And so part of the game is that somebody has to go to site and start it up. And that should be someone that's very familiar with plants and how they should work, and maybe not the installer. So that's all kind of part of the scheme of this implementation. So we're not the only company creating packages. We're just really one of the first. We are doing this at a place in Olympia, Washington called the Eklund Innovation Center. The guy whose face down in the lower left-hand corner, his name is Kenneth Eklund. He's pretty much the reason why we have CO2 water heating in North America. He started this work in around 2012, funded by all of our utilities up and down the coast. And he brought the technology from Japan, placed it over here, and started that long process of learning. So you know, it's recognized that that's what is his contribution. But doesn't this look familiar? Lower right-hand corner. Heat pumps are on the back. Heat pumps are giving all of their water, high temperature water, to that big primary storage in the left-hand side. Primary storage is piped over to that swing tank. And then if we can drill in any closer, we'll see that there is a recirculation pump on board. There's a temperature mixing valve on board, or a temperature maintenance valve on board. The red tank is expansion. Everything there is on board. The gray box hanging off on the right-hand side is the single landing power. So in these modular or prefabricated systems, you connect power to the service panel. Service panel is, you're able to lock out individual heat pumps, no matter, you know, kind of the type of heat pumps you're using. And then that power is given over to the heat pumps, and there's a controller box that's kind of hard to see in the upper right-hand corner of that lower right-hand picture. And the plant's just ready to start up. It can drop on site. The installing contractor is responsible for hooking up 3 water pipes, and the electrician is responsible for landing 3-phase power in this case. And then a factory trained technician shows up on site and starts the plant up. It is, see if I can get my slides to jump forward. So if I go back and I look at this, the configurations that the industry can work with, there's another packager called Origin in North Dakota. And the two companies offer very, very similar solutions. So this particular skid in the lower right-hand corner, or this skid that we're looking at the screen, has all of the things that a plant needs, but it's only got so much storage capacity and so much heat pump capacity. But we've got the power landing, we've got the recirc pump, we've got the swing tank, we got the controller, we got the temperature maintenance valve, we got everything we need for a basic plant. If we want to increase the size of that plant, all we do is park it next to another skid frame that's got more primary storage, maybe some expansion room in those red tanks to add expansion capacity for the increased amount of primary storage. And on the back of the frame, it's got more heat pumps to match that new increased primary storage. So that's primarily where the industry is going. And this was really one of the design intentions and the output intentions or goals of the Advanced Water Heating Initiative, the commercial work group, because it's an affordable way to implement heat pump technology into buildings. And if the utilities are going to incentivize it, they really, really want to reduce risk. So if they're saying, hey, you're going to build a plant and it's going to have an average seasonal capacity, a seasonal COP of 3 or 3.5 or something like that, we might give you the cost differential between 3.5 COP of your building and what your building would be in electric resistance, right? So we can incentivize that as a utility and give you that money. We just want to make sure your plant's really going to do 3 COP or 3.5, and don't give me a dud that does 1.75 or 2, right? Because our funding's based on that capacity. So it's a risk reduction move. And so as you start looking at it, I can show our examples, but there it is. That's an entire mechanical room. There's a building in downtown Seattle that we looked at earlier that had the startup technician looking at a controller and a clipboard and so forth. And that system was a little bit bigger than this one, maybe 2 of these skids, but it had a whole nother floor built on top of the roof, or a whole nother wood frame housing built on top of the roof to house the domestic hot water system. Didn't really carry anything else, had a couple of vent stacks in it and stuff like that. But that's super expensive to design, permit, and construct that wood frame, and then have installing contractors bring in tanks and heat pumps and copper piping and build the whole system on site, where with prefabrication, we can just literally set this box on the roof. It's in an insulated, weather-tight enclosure. It has everything that we need. We can see the heat pump, expansion tank, the building connections in the lower left, 3 water pipes, cold water in, hot water out, and recirc return. On the other end, it's got a big old service panel. And we got a recirculation pump, a swing tank. We've got a master controller that'll stage the heat pumps and send alarms. It's in an R8 aluminum, R8 insulated enclosure, because if we're going to put it outside, we want to add a little bit of insulation to it. It's not mandatory, but it certainly is good practice, because that wood frame is probably insulated at R20, and maybe that R20 is effective or not, depending on the frame style and the existence of continuous insulation. In any case, we want to add some more insulation on top of the R12 primary storage insulation and work it. So as we move forward in the industry, you'll see that there'll be an offering of different sizes of skids for big buildings and small buildings. You can only make skids so big, right? So you're going to pick your recovery based on the eco-sizer outputs. You'll match it up with the storage, and hopefully there'll be something there. There's another move afoot with existing buildings, which is pretty interesting and pretty valid, and it's a part load system. So I see in some markets there are building owners who are motivated to decarbonize their building. They've got an existing boiler, they've got an existing distribution system, but they just want to reduce the amount of gas fuel going into that building. So it doesn't mean they have to replace the entire system and everything becomes heat pump. They could give a number and say, I want to cut my GHC in half. We've done a couple of buildings like that, big buildings. And so essentially we can strip down a plant and it would have no swing tank, kind of like the one we were talking before. And we can take heat pumps, pair it with primary storage. We can do a sizing to cover a percentage of daily load, and we can direct that sizing into their existing plant And now the existing gas boiler or whatever infrastructure is there, maybe it's a little bit updated and the recirc pump's a little better because you got the odd opportunity to fix it. But in any case, now we're contributing ahead of the load of that building. So, and if a boiler just sees incoming water temperature in conditions that it wants, it doesn't need to fire up a boiler, right? So that's a way we can reduce the GHC. So that's a part load system. That's a real thing. And then a series of small heat pumps racked together to act as large heat pumps, like that building in California, a range of sizes. But how do we start applying this to big buildings, right? In big buildings, we have a choice and we have more large capacity heat pumps going on. So we can create some really big zones, pair a heat pump to it, and on we go. And, I'm working on a building in Vancouver, BC right now, 2 80-story towers. And one of the zones is 62 floors. So that's quite a lot of capacity to serve, but we'll wind up serving it. Or another way to look at it in big buildings is zone them. This building is a project we're doing in Menlo Park. I think it's around 300 units, and it's just got multiple plants on top of the roof. And each section of the building is zoned for 100 occupants or 100 unit 100 occupants. I think it's, as we look at it, as occupants, because the units don't use hot water, it's the occupants that use hot water, right? So that building has been zoned, and when you zone a building in this way, now you've got a smaller, more compact distribution system. You've got redundancy across the building, and a smaller compact distribution system, a little bit less heat loss, a little less pump energy, a little easier to control, and we don't have to work with those super big pipe diameters and higher pressures, and there's a lot of things when you kind of downsize and right size. So a lot of different ways to approach this. So there ends kind of the slide deck. Okay, so I'm flipping over. Only one question. And Garrett Connell, to everyone, does the roof skid have a cadet heater for freeze protection? Depending on where it is. It's a great question. We're actually grappling with some of these questions right now. So if we go back and look at this one, so this one's, I was going to jump a couple back, right? So the whole thing's wrapped in an R8 enclosure, and it's continuous insulation. And because I'm designing it, the insulation is cork, natural cork insulation, R4 per inch. It's got some nice density to it, and I'm just not a great plastic foam fan. So in any case, we think about what's going on in here. We've got a primary storage tank that's holding 150-degree water with R12 insulation. Everything in here, all the piping is going to be well insulated, but you just can't get the insulation around everything, right? There's always just kind of nipples and things that are hard to insulate. I don't know how. I assume that tank skirt is welded directly to the tank frame and there's no thermal break in it. I think we're going to make a lot of heat in this thing. And so we're deploying in this system, we're using it as an educational piece. We'll deploy an additional outdoor air temperature sensor, but actually put it in the enclosure, because I think in California, we might make a little bit too much heat, and I might have to think about ventilating. And I'm not real happy about that because I don't want to push the heat outside. I want to save it, put it in hot water, and keep going. So we'll find out what the conditions are. In a cold climate, I don't think we have an issue. I think on the inside, because I still think we're just going to leach a lot of heat. We certainly can put in a heater, but we don't think we need one yet. We're just making our first package delivery, so we're still learning here. What we do is heat trace the connections from the the inside of that enclosure to the outside of the heat pumps, right? Because in freezing conditions, we need to insulate piping. And the reason these, if you look at the NEA list right now, and really any of the data, but the NEA list shows that this particular heat pump that we use has the highest COP in the industry, over Mitsubishi, over Lars, over anybody else. And it's because it's a potable heat exchanger. And so we don't have a little loss going from a heat exchanger in between the actual heat pump and the primary storage, because we're 100% potable system. And so Len, okay, so Nick says amazing. Yeah, thank you. And then large apartment buildings, heat pump, water heating system, typically roof or parkade and garage. Len, that's a yes and yes. Roofs, it just depends on the building. There's lots of interesting things going on. We're looking at existing buildings in California, small low-rise apartments, where there's no room to do anything. So we're making a nice enclosure that sits outside next to the building. We've got a lot of systems going on roofs. We can put the same system in a parkade. It'll slide in an 8-foot clearance. And typically in most parkades, that's fine if we can get in there before the fire sprinklers are up. And we can place it on, low profile skates and skate it in. So, and then if that's a problem, then we can kind of break the heat pumps away from the tanks and start heading more towards a site built system so you can bring all the equipment in. Yeah, Phil, how do you deal with water created by the defrost cycle in freezing temperatures? So things are changing there a little bit, but the current plan, the current class is that we have a heat traced condensate collection point, and we bring all the condensate together from all the heat pumps outside. They're heat traced. We've added heat tracing inside the units too. We keep it in liquid form and we direct it to a single point pipe where the building can receive it and drain it. There's there's an additional feature coming on with a heat pump that I work with, and it starts removing condensate drains, but I don't fully understand it, so I can't really speak to it yet. And then Brian's asking, what are the vibration isolation requirements for room top installations, or probably rooftop installations, for acoustical requirements? Well, so that's an active question right now. What you saw in the pictures didn't have much vibration isolation. And so we made a revision to current product lines. And at least in what we're producing, we've added some vibration isolation units onto it. We're not thrilled with them, but we're doing it. And it's going to vary across the heat pump. For us, I have one answer. If we're using a Mitsubishi, it's going to be a different answer. If we're using a Lars, it's going to be a different answer. It's a little bit situational. I can speak to us. I can't really speak to the others. For us, I know this heat pump really well. It doesn't make any vibration. And when it's operating, it's 37 dB. So you can literally put it everywhere. And it doesn't create any vibration. However, we are putting isolators on it because good practice would say, and the engineering community is ready to receive it with vibration isolation. They can't really see a heat pump that doesn't make any vibration. We've got data, but it's easier to actually put the isolation on than try to kind of convince or bring out new information and so forth. What are the vibration isolation requirements for rooftop? Okay, I think I just answered that. And then Zach followed up with service pros and cons of water drop versus larger single units. Oh, that gets into a little product specific, so I'll stay light on that because I'll just stay light on it. So in the products that we're working with, the service, everything's prefabricated, And the nature of these particular heat pumps are pretty light. So there's an annual service plan. It's pretty light, blow the coils, maybe inspect the plumbing and look for leaks, check for alarms. The controller has an alarm log. So even if you don't get notified of an alarm, it'll give you a CSV on full behavior and run cycles and things like that. The system is able to be valved off and washed and push fluid through it. Strain reliefs exist, so they can be opened up and inspected. Your mesh strainers. Not really a lot. The weakest link in the system so far in any of these systems is probably going to be the electric resistance heat pump. It's not running like a regular commercial water heater. It is a commercial water heater, right? So they always have kind of a shorter lifespan, and then we'll see the heat pumps are going to just vary on how the system is sized, what the conditions are, and we got to make sure that we're operating within reasonable water pressures and water conditions. So a little light. Site-built systems will be, a little bit different. And if it's bigger and more complex, it'll probably have a few more service points, but it's still just a heat pump. Aaron's asking what sort of factory testing occurs to ensure system functionality to specs to reduce risk. Well, pressure check. As far as functionality to specs, for us, the packages that we're creating are the same packages that we've done in site-built systems for years. So, so there's not really a lot that we have to do because we already know, and the utility knows how these systems work. It's just, can you get it to site without a leak? And can your installing contractor get it set up? And at startup, we'll actually see the functionality. Start up on a system, no matter whose system it is, it takes a day. You show up on site, you make sure the whole system's wet, start up the heat pumps, watch primary storage build. Depends on what kind of controller and visibility you have in the system. Watch primary storage get built up and then into the swing tank. Ideally, you've got a load. And if you've got a load, then you can start working with the temperature maintenance valve and things like this, and what is the interface to the controls. There was a screen way back there that had a small screen that's a little LCD screen, and it will vary. Each heat pump is going to have a different set of controls, and they're all going to have some kind of LCD. As things get built out with more CTA 2045, that'll kind of change the nature of the screen. We'll need to be able to see more data points, and you just might see larger, 8-inch LCD screens on top of controllers and things like that. So Nick is asking, how does an installed cost of a water drop system compare to a gas boiler plus solar thermal preheat system that is traditionally? Boy, I'm not going to be able to answer this. And it's a little bit market dependent. And Nick, sad to say, I could not speak to solar thermal preheat systems, nor installed costs of gas boilers. I think the utility packages or the incentive packages that the Advanced Water Heating Initiative and the member utilities that are members of that are developing their incentive packages to try to right size that cost relationship. I know the one thing I can speak to is I know that building a site-built system is expensive because site time for plumbers is not really the most efficient. The tools are, you're working in a mechanical room, it's hard to get stuff in and out, and there's other issues on the construction of the building going around. Prefabrication in a shop is really straightforward. It's kind of the same task day after day. And so, right now for us, we've got 25 skids going through the shop right now. and they'll just keep cranking skids out, you know, same, give it a pressure test at the end and send it to site and start it up. And yeah, you guys are better at evaluating costs. It's not really, it's not my expertise. I just know how to make 45-degree water, 150-degree water, and push it through a pipe. That's kind of my one trick that I'm good at. Okay, so how are we doing? I think we're well, 8 minutes left in our 2-hour session. Any more questions or points to discuss? Delivery time for a skid system. Brian Rasmussen. You know, actually pretty good right now. We've got work going on, at least in our shop, throughout the year into the fall, but we've got a capacity that we can add more projects into it. So I'd say our standard lead time right now is about 12 weeks. And that would be based on, you know, kind of a stock product that is presented as a standard catalog item. There's a website and a catalog and you know, a bunch of plants that you can choose. And if it's one of those, then yeah, about 12 weeks. Cold climate packages Northeast, and is there any significantly different about them from what you've shown? So we don't work in the Northeast right now, less, and I wish I could. I'd really like to. You know, New York and New England has been on our radar. We've had lots of inquiries from that region. We're a West Coast company, at least for our company, and what we're building is really suitable for climate zones, you know, 3 up through 5. Sure, 6 is kind of a question mark. I don't think we're ready to deal with 7, and because we're in the first 2 years of these, we kind of own the success of the skids. If there's a problem, we go on site and deal with it. And so I don't think we're ready to get on a plane and go to the East Coast. So cold climate packages, so CO2 is your friend for sure. And if you're in cold climate, 7, something like that, you can make 150, 160, 170-degree water all day long. And you would be looking for a heat pump that has, you know, maybe a glycol loop between the heat pump and a heat exchanger in front of the primary storage. That's what I would really do in those climate zones. That way, you lose a little bit in COP because you've got the heat exchanger in the middle, but it allows you to work in much colder climates. So that would be a larger heat pump like a Mitsubishi 40 kilowatt, or one of the larger Lars systems, or any of the new CO2 large plants. The stuff that we do is really a potable system all the way through. And so I've got it in way north in Smithers, BC. And every year the challenge there is to keep the defrost from freezing up and causing a problem with the system. And that's about as cold as we want to do with a potable system. And then we can start looking at, we can kind of do our own research and development in how to turn it into a glycol loop and still retain the same. But if you're in the Northeast and in climate solid 6 and 7, I would work with a larger capacity heat pump with a glycol loop and a heat exchanger away from primary. And there's, the good news is there are products to choose from now. It's just hard to find the designers and the people to help you design a project successfully. All right, how are we doing? 100 and, yeah, okay, a few more minutes. We'll give it a few minutes. Any questions pop up? And if they don't, we're 2 minutes away from 11 o'clock. And, you know, thanks for joining, and I hope this was helpful in understanding what we're looking at in the transition from the source of fuel we're using and the types of systems we're using right now into fully electric heat pumps. We can definitely do it. There's been a lot of work the last couple of years, and this AHR show showed that the last couple of shows, the industry got the message saying, well, if you want to sell a heat pump, you better have CO2 if you want to make domestic hot water. Because this year they all showed up with new CO2 products, either introduced or planned, and we're going to be able to do this. And our company is just one little part in this. There's lots of other companies and lots of other capacities that are being built. And Brian, that is going to be up to ITIL, and 3C Ren will share the PowerPoint, and then Eva's suggesting I share my contact info, and maybe I can just write it right here. It's really simple. Albert, well, see if I can write and talk at the same time and do a Zoom. That's a talent that I wasn't really trained for. Albert at smallplanetsupply.com. And we'll see if we can maybe share that with the slides and a follow-up email. And then if you really want to look at maybe what we offer in WaterDrop, there's a website, waterdropsystems.com or smallplanetsupply.com, and you can kind of find your way over to the WaterDrop section. It's an entirely new division of our business at Small Planet Supply, just for big building water heating. So we're right about 11 o'clock. I think I'm going to wish everyone good morning, and hi from Olympia. Thanks for joining. And, you know, for all of you in other places, I'm seeing a little bit of snowflakes outside. So, there we go. And that's probably nothing to fill up in the north. So thank you very much.
Thank you, Albert. Thank you, Eva. And yes, I'll follow up with everyone with slides and the recording of today's video. If you have any questions regarding learning units, I'll drop my email as well. Feel free to reach out, and a little bit more too about our multifamily incentive program. I'll drop the link on the chat as well if you want to learn a little bit more about what we have to offer. But with that being said, I'll let you all go, and thank you so much for your time today. Thank you, Albert. Thank you, Eva.
Thank you, everybody.